the subject of today's lecture is spin. Yesterday we briefly introduced the apparatus that Stern and Gerlach used to actually reveal that silver atoms, okay, in fact form two strange spots on a screen, okay? Nowadays we know that those two spots are silver atoms with spin up and silver atoms with spin down, okay? Somehow separated by this kind of filter. Obviously, you can use this trick, okay? So if I have the apparatus, okay, I told you that there is a particular shape of the thing, but suppose that I now draw here the north and the south pole, then if you use this apparatus, the silver atoms come, they are deflected, okay, and here they end up in two spots, here and here, okay. As I told you, the spin up come here, the spin down come here. This is a screen and you block everything. But you can play a trick now. You make a hole, okay? If you make a hole, only the spin up comes out. For instance here. And you assign to this filter, this whole box, a line which is essentially fixed by the magnets, okay? So with this clear direction in the particular hole, you can select systems with spin up only coming out, okay? While blocking everything else. A bit like when you have a polarizing filter, okay? All the photons that are wrongly polarized with respect to your glasses are simply blocked, okay? Good. Obviously, you might do the opposite, but that's what you can do in practice. And we will play with this object, imagining experiments with repeated filters, okay? So later on, more about this. But for the time being, let's concentrate on these two states, okay? So we discovered that there must be some other angular moment, some other degree of freedom which has only two possibilities, and we discussed yesterday that indeed angular momenta allow half integer angular momentum, which in particular in the smallest example s equal to 1/2 would provide you two states, okay? Obviously a few years after the discovery, Dirac actually understood the origin of this object, which is intrinsically relativistic, by the way, appears out of the Dirac equation in an appropriate limit, but we don't care about it. We simply say, okay, there is an angular momentum, okay, I'll call it S, an operator. It has the value. Before I was calling J, now I will call it S equal to 1/2. Obviously there are three components of this thing, okay? I can form S squared, I can form SZ, okay? And I know that I have states, okay, which I will call S equal to 1/2. And then I will use here M. Okay, this M could be minus 1/2 or 1/2, right? The value of S squared, okay, here again H bar has been eliminated by just dividing every operator by H bar, okay? So here I know that this is S plus 1, okay, times, let me abbreviate this. This is 1/2 M. And here I have 1/2 M, 1/2 M. Okay? Good. Now, again, this number here is 3/4. You see, because if S is equal to 1/2, you can calculate easily this number here. Fantastic. Those two spin states, I need to abbreviate them. they are too long to write. Okay? Let me just invent a shorthand. So the state with S equal to 1/2 and M equal to plus 1/2, okay, which is the eigenstate with Sz equal to plus 1/2, I will call it plus Z. Z to remind us that this is an eigenstate of Sz, and plus to remind us that there is a plus here. Sometimes, if there is no ambiguity, I will forget about the Z sometimes, or maybe I will use this notation, okay? Spin up with an arrow up. Another useful thing is for the S equal to 1/2 with M equal to minus 1/2. Then at this state I will associate the following symbol, minus Z, and if there is no ambiguity I neglect the Z, or I might use the arrow down symbol. Okay? All of these are perfectly allowed. Now, that's the word of this angular momentum. Two states only. That's the smallest Hilbert space that you can think of. There is nothing smaller than a two-dimensional Hilbert space, by the way. A one-dimensional Hilbert space, it's dull, because there is only one vector. You normalize it, it can move. Okay, so there is nothing you can do in a one-dimensional Hilbert space. But in a two-dimensional Hilbert space, there is a lot of physics, and in fact, it is the simplest setting in which you can do quantum mechanics. For some reason, it comes out to be always undigested. Okay, that's an experimental fact. Consistently, all the diploma students of the past years had some kind of difficulty in working with spin. Maybe because somehow you have seen previous courses on quantum mechanics with wave functions, the wells, the harmonic oscillator, and spins are less studied for some reason. But I want to convince you that indeed it is the perfect system, because you have simple 2x2 things to do in most cases. Okay, and that's very convenient. So no infinite dimensional matrices, no truncation, no nothing. Okay. So here is our Hilbert space. I would call it H spin. Okay, it's essentially made of states that are, I will call them psi spin, and they are simply combination of these two states. So I will call it Z plus times plus Z minus times minus. These are two complex numbers. Okay. As you remember, you can make complex combination of the two basic. So the two basic states are this. Okay, and you can make any combination you want. Do not confuse the Z here, which is this direction, with this Z, which is complex number Z plus and Z minus. Okay. Sorry for the ambiguity of notation. Now, if I ask you, please calculate for me Z plus and Z minus, you know that there is the usual trick. Calculate the scalar product, right? So I can calculate that Z plus minus is simply the scalar product of the state plus or the state minus with the spin state that you have. Okay? Obviously, normalization, okay? So if I want psi spin equal to 1, okay? Then since these two states are orthogonal to each other and they are normalized, supposedly, then you can do the calculation and you discover that this is Z plus modulo square plus Z minus modulo square. Okay? So if I want normalized spin states, two complex numbers are too much. You can impose a normalization condition. The square modulus of those two complex numbers should be set to 1. Okay? Is it clear? Very nice. Now, obviously, this is a basis, okay? So I can express psi spin equivalently as a column vector, okay? A column vector with two components, as we said in general, so an element of C2, right? And what are the two components? Z plus and Z minus. The component on this and the component on that. Okay? So an element of C2 with this normalization in place. Fantastic. Now, where does the spin enter in our Hamiltonian so far? Well, we have not seen it. Because a couple of reasons. The first is that we never discussed effect of magnetic fields. Now, if I have any Hamiltonian of an electron or something, okay, something with a spin, and I ask you, okay, now there is a magnetic field, how does it enter the Hamiltonian? Then you might say, okay, I know about the orbital degrees of freedom, but now there is a term that couples essentially the magnetic field to the magnetic moment, and you know that the spin is a magnetic moment. We discussed, I mean, it feels the magnetic fields in the Stern-Gerlach experiment. Now, here in front of this thing, there are two constants. One is the Bohr magneton, okay? The Bohr magneton is essentially the quantum of magnetic moment. If you remember, yesterday we discussed that even in classical electromagnetism, if I have an electron orbiting, a charge of minus E orbiting, then you expect essentially that I have minus E times the angular momentum divided by twice mc, okay? So if you, this is an angular momentum with dimension, okay? So if I imagine somehow an angular momentum of order h bar, then the unit, the natural unit of magnetic moment is E, h bar divided by 2 mc. You see? Okay? So this is the Bohr magneton. In this way, h bar is already accounted for here. So S here is dimensionless. Okay? Don't forget. Okay? So there are no h bars here. They are already here. Okay? Good. This is the magnetic field, and this is the spin operator. Now, what about G0? G0 is roughly 2. Okay? For our purposes, will be always 2. Okay? But there are situations in solids where you should be aware of the effective G factor in bands. I don't discuss those things. Okay? Now, where this comes from? Dirac. Okay? Dirac discovered a 4-dimensional object to treat properly relativistic effect, and if you take the non-relativistic limit, there comes the spin automatically out. Okay, let's take it. That's it. Not really. There are other terms, okay, in which the spin would appear, but they are small. Again, relativistic effect. Okay, now later on, we will discover that even in absence of magnetic field, there are terms that involve the scalar product of the orbital magnetic moment and the spin magnetic moment. They are called spin-orbit effect. Now, they are all small. As these are small. You see there is C there. Okay, they are relativistic effect. Okay, so to the lowest approximation, they produce small numbers, but certain times they're very important. Okay, so nevertheless you have to account. So we'll learn how to deal with those things in perturbation theory later on. For the time being, I was just willing to stress to you that even in absence of magnetic field, in principle, the spin makes its appearance, okay, and multiplies the. But so far, we have disregarded those things, and I will continue to disregard them. So let me just consider this effect. This is, by the way, called Zeeman coupling. Now, you might say, but what are you talking about? Here I have a two-dimensional Hilbert space, while this object works on wave functions, okay, so on space of functions. How do I match the two things together? This seems to be not the right setting to describe, to write an Hamiltonian. And now I will teach you how to glue together the usual Hilbert space related to the orbital degrees of freedom, which is space of functions, with the Hilbert space that I have just introduced, which is the two-dimensional spin Hilbert space. Okay? How do you glue together those two things is our next goal. Now, to do that, I will introduce. Okay, so let me just forget about this for a while. Let me introduce the concept of a tensor product of two Hilbert spaces. Okay, so suppose that I have two systems. One system I call it A, and one I call it B. And I have associated to them a Hilbert space, H of A, and the Hilbert space, H of B. Okay? Then there is a concept in mathematics that is called the tensor product of the two Hilbert spaces. Let me tell you what it is, okay? I will be very, very crude maybe, but not too bad. So let's imagine that I have a basis for the Hilbert space 1, okay, A. So I'll call it phi A of M, okay? Possibly infinite dimensional, whatever. And then I will have a basis for the part B system, and I will call it phi B N. Okay? Good. What is the tensor product? It is an object, okay, whose elements of the basis are pairs. Okay? So let me write it like this, and then I will illustrate it in some examples. Okay? So elements of the tensor product are simply product objects with all possible phi A of the space A and phi B of space B. Okay? You might say, what are you talking about? Take it for a second. Okay? These are elements of the basis. Yeah, product with this funny product thing here. Remember that in the end I would like to have, for instance, wave functions and spin. Okay, so they are not quite the same thing. Nevertheless, you can consider them together as pair of states. Okay, but if this is a basis, a general state belonging to this product here is given by sum over all possible m and n in this setting here, some coefficient, let me call it psi mn, times phi A of m, phi B of m. Okay? Is it clear? This is a basis, and therefore this is the element of this general vector. How do I calculate a scalar product? I have to introduce a scalar product, right? So, the scalar product of two elements, say psi and phi, where phi is written also as a kind of general combination like that, is calculated in the following way. In principle, it would be a sum over m and n, m prime and n prime, of what? Psi star m n, phi m prime n prime, okay, or vice versa, whatever. Okay, let's write it as in the notes, like this. And then I have what? I have the phi A m prime, which this lives in space A, okay? It takes the element of A and you take a scalar product with it, okay? They don't look to B. A looks to A. And B looks to B. Okay? That's the rule. Okay? So you calculate the scalar product in this way. Obviously, in this case, if this basis is orthonormal, you can use here a delta n prime n, and here a delta n prime n, and therefore the expression is much simpler. You can write it as sum over m and n psi star m n times phi m n. Okay? Good. Examples, otherwise we are too abstract. Now, let me start with the simple. Suppose that I have a particle in 2 dimensions, one particle only, but in 2 dimensions, okay? So, for me, A is the Hilbert space of the function of x, and B is the Hilbert space of the function of y. After all, I want to describe a particle on the plane, so x and y. So the wave functions are functions of x and y, but I can view somehow the functions of x and y as obtained from function of x and function of y, right? Now, obviously you might say, okay, so here somehow I have a Hilbert space h of x, which is made of wave function phi m of x, okay? For instance, harmonic oscillator states, whatever you want, okay? Then B is the h of y, which is made of other states, possibly different. They do not have to be, so I should in principle here use, these are the x states and these are the y states, but I mean, somehow the variable here suggests that I might take a different, for instance, this might be plane waves in the y, and harmonic oscillator in the x. Doesn't really matter. Use whatever basis you want for the x and the y. Okay? Good. Now, the writing that I have written here suggests that this function of x and y, okay, should be possible to be written as a sum over m and n of a coefficient times the phi n of x and the phi n of y. Okay? So in principle, given the basis of x and y, with appropriate coefficient, I can express any function of x and y. You might say, okay, so what do we have? Well, one thing to notice. In general, although the 2 spaces have separate bases, this function here is not separable. You cannot split as a product of a function of x and function of y. What is the condition to get a separable state? Well, certainly, if I have that the coefficient psi mn are equal to, say, some f of n some times d of n, okay, product, so the coefficients are themselves written as product of 2 different objects, then you can immediately see that I have a sum over m of fm times phi m of x times a sum over n of dn of phi n of y. Okay? Now, this is in general some function of x. Okay, sorry. I didn't want to use, never mind. In the notes I do some confusion. This I call it g, f and g, okay? And then therefore this is g. Okay, so this is a function g of y. So you see that if the coefficients are factorized, then the resulting function is indeed a product of a generic function of x times a generic function of y. But, in general, if this is not factorized, the function that you obtain is a real, genuine function of x and y. Okay? So you see, I was able to generate somehow the two-dimensional Hilbert space, two-dimensional. All Hilbert space of functions are infinite dimensional. But the Hilbert space of the two-dimensional particle by taking a tensor product of a Hilbert space of one-dimensional particles. Okay? The particle is the same, by the way. I'm not considering two different particles, the same particle. Okay? With the same technique, I might consider more than one particle. And in fact, later on, when you will do many particle system, you will have to somehow glue together Hilbert spaces of the different particles together. And there will be the issue of indistinguishable particle and what statistics should I use, should I impose to the wave function. All these things you will learn later on. But the actual gluing together through this technique of taking tensor product is a kind of general tool, okay, which works, you see, very well, even if I have this essentially one particle and two directions in space. The second example that I want to do is one particle which has orbital and spin degrees of freedom, okay? So in the second example, which will be important for our discussion, A is the orbital, okay, and B is the spin, okay? So H orbital is obviously generated by some function of x, some just wave functions, okay? While this object here are generated by these two objects here, okay? So the plus and the minus. And I will call them sigma, okay? So sigma can be plus or minus, okay? Are the states, the two states that I have there. Good. So let's write now with the same technique the most general state of the tensor product of the, so this belongs to the H orbital tensor product H spin. Okay? Let's write it. Will be a sum of, I'll try to follow the notation. Sum over, well, let's call it n. Sum over n, sum over sigma equal to plus or minus. I have two of them. And then I have some coefficient psi and sigma, okay? And then I have the state phi n there, tensor product, the state sigma for the spin. Is it clear? Okay? So this is the orbital and this is the spin in this setting that I told you to consistently write. Now, let's try to write a real space representation. So, what is the, how to obtain a real space representation? In general, I have to take a scalar product with position eigenstates, right? So, such an object is a position eigenstate of spin sigma, okay? So I glue together a position eigenstate with a spin sigma. Now I take the scalar product of, let me abbreviate it as x comma sigma. Whenever I write something like this, okay, what I mean is actually this longer writing. So x comma sigma, scalar product with psi, written there. Remember how to take a scalar product. The x looks at the orbital parts only, the sigma looks at the spin part only, and then you follow the rule. You do it, and you realize that this is equal to sum over, say, n, sum over sigma prime equal to plus or minus. Then I have the psi n sigma yes, psi n sigma with phi n, okay, and then I have sigma, which is what I have here, with in general sigma prime. In other words, here I added an index, okay, to distinguish it from the sigma that I want here, okay? So I'm summing over sigma prime, there it is, sigma prime, okay? Good. I have to take the scalar product with sigma. Now, this implies, obviously, that being these two states orthogonal, there is a delta of sigma and sigma prime. Here is sigma prime. And therefore, this is sum over n of psi n sigma. This is the wave function phi n of x. And this is just a delta. And that's it, right? Yes. Fantastic. Okay? This combination of wave functions summed over all n, you see, the only free number is psi. Okay? Let me call it, is a definition, the orbital, the spinor orbital with sigma projection. Okay? Good. Now, if I ask you, please write psi as a spinor like this. Now, if this was only a spin, you would write a two-component vector like this, elements of C2. But if I ask you now, please write a matrix form of psi, all you might say is, okay, I have a two-component wave function. One is psi plus of x, and the second is psi minus of x. Okay? So this is a two-component spinor wave function. Notice the difference with this. These are two numbers, these are two functions. Okay? But the two functions are different in general. Okay? The psi plus and the psi minus are different. Why? Because in general this coefficient here is not factorized. If it is factorized, okay? So suppose that this object, okay, was indeed the product of something for n and something for sigma, then you immediately realize that what comes out is that this object here is simply factorized into some z sigma times an orbital wave function. Okay? In other words, if there is factorization, this object is also factorized into psi orbital of x times a spinor. So the same orbital appears here and here, and there is z plus, z minus. Okay? Is it clear? Good. So in some sense, when there is factorization, I would write that psi is equal to psi of the orbital times psi spin. Okay? But in general, the combined Hilbert space tensor product allows for states which are not factorized in this form. Okay? Pretty much as the two-dimensional Hilbert space is not product of is not made only of functions that are x times y. Okay? And here again, spin orbitals are in general not factorized as orbital times spin. This is what happens if you account for the spin orbit Hamiltonian that I discussed before, by the way. The thing is not factorized. In some cases, however, you can disregard those terms and factorize things like this are a good description of your system. But this depends on the situation. Now, having introduced this, let's see, what does this mean? Okay? Obviously, this means an operator that works only on the orbital Hilbert space while it acts as the identity in spin space. Okay? So this is just a compact way of writing something which looks at the orbital part only and does nothing on the spin part. Okay? And vice versa, you see that this works on the spin part only, and obviously it multiplies the identity in the orbital space. Okay? So in some sense, these are compact ways, ignoring identities, of writing an object that knows how to operate on a tensor product of orbital and spin by just operating on the orbital part with the standard Hamiltonian and operating on the spin part with this piece of Zeeman couple. Okay? So, written as such, this object is an operator in the tensor product space. Is it clear? These things are, I mean, not straightforward to digest. It takes a little while. Okay, so I was very slow on purpose. Okay, although they are not difficult, I can guarantee. Okay. Very often, I will actually disregard these fancy signs. Okay, but you have to always think what they are. I mean, if I write something like this, okay, what I mean is that this object lives in this space, the second piece lives in that. They are close together. They are not ordinary multiplication, okay? You cannot multiply a wave function times a vector of C2. But they live in different space. They stay close together. No? Whatever operator you have to apply, either you apply to that or to that, and they peacefully go on. You can just do scalar product and things like this. Okay? So don't be worried about what is the meaning of that product. It's pairs, okay? Pairs of things, and you work with them peacefully. Okay? Good. Sorry for this long introduction of tensor product. We started later, so we can do a little bit. No problem. Okay, good. Now, let us now return to our simpler looking thing. So a two-dimensional hyperspace for a while. So we'll forget about this complication, which will come out in before the end of this week, of this lecture today. Okay, I think. So suppose that I ignore for the moment the orbital part, and I ask you, let's write matrix element of the spin operators, okay, with the usual technique. Once you have a basis, okay, you can write the states as two component vectors. The operators are 2 by 2 matrices, right? Let's try to see what these 2 by 2 matrices are. Okay. Okay. Now, so I want to write now the matrix elements of sigma x, the matrix element of sigma y, and the matrix element of sigma z. Let's start from this. Sigma z is simple. Okay? Now, here the element, okay, sigma z in between, say, sigma prime and sigma means simply taking this, okay? Okay, now, since this is an eigenstate of sigma z, okay, with eigenvalue of m, which I'm calling, by the way, so m, yes, m is 1/2, okay? But, so it's sigma divided by 2. Sigma is only plus or minus, plus 1 or minus 1. Okay, so this object is, say, 1/2 times the delta of sigma prime, because I essentially have the scalar product of the two elements. Okay? So 1/2, sorry, I was too fast. 1/2 times sigma. So if it is plus, it's plus 1/2, otherwise it's minus 1/2. So to be explicit, the matrix that I have here would be just 1/2 plus 1 minus 1. Okay? Is it clear? Good. How do we obtain the matrix of x, Sx, and Sy? Well, the best thing to do is to return to our friends S plus and S minus. Remember what they are. This is Sx plus I Sy. Okay? And this is S minus, like that. The ladder operators. Now, what I know is that if I take S say plus, okay, and I apply it to the state minus, I obtain what? The state plus with the square root factor. Shall we calculate the square root factor? The square root factor, the general expression is j plus 1 minus m times m plus 1. M is obviously equal to, this is the lowest object, so this is m equal to minus j. Okay, so it's let me write it, m plus 1. Okay, and put here, this is 1/2 everywhere, and this is minus 1/2. If you do your honest calculation, it's very, very, very trivial. Is the square root of unit. Okay? So here is no actual factor. Good. Because it's 3/4 plus 1/4. I mean, it's a very simple thing. But let's just jump over it. Okay? So believe me, it's square root of 1. Okay. In the same spirit, S minus of plus, okay, you reduce it to the minus, and there is a square root, and again, a square root of 1. Okay? So I know these two things. Knowing this, the best strategy to calculate the matrix element of Sx is in fact re-express them in terms of S plus and S minus, because I know how S plus and minus act on the elements, and when I take the matrix element, it's 1 second calculation. Okay? So let's first calculate Sx, okay, sum these two things is equal to 1/2 S plus S minus. Is it correct? Yes, right? Good. So let me just take the matrix element between sigma prime and sigma. So this is 1/2 sigma prime S plus, okay, sigma plus sigma prime S minus sigma. Okay? Let's try to see. So suppose that I want, say, the element, let me write it here. This element here. Okay? So the element let's start with the diagonal element here, the plus. Okay? Now, so here there is a plus and here there is a plus. S plus of plus is 0. S minus of plus is plus, but if you have here a plus, S minus of plus is minus, but then I have the plus here, and therefore I get 0 again. So the elements on the diagonal are 0. If I calculate the element psi plus minus, means that here I have a plus and here I have a minus. Now S plus of the minus state is the plus, right? Here. And here I have the plus, so here I have 1. Okay? Good. If I do the calculation of this element, I will get again 1, because it must be a Hermitian. So whatever you have here you must have there. Okay? Good. But there was a factor 1/2 here. Okay? So the element, the matrix, okay, of Sx in the end, okay, results to be 1/2 0 1 1 0. Okay? This object here is a name. It's called sigma x. It's a Pauli matrix for this spin x. Okay. While this object here, by the way, is called sigma z. Okay? The Pauli matrix along z. Okay? What it misses is the sy. Do a similar calculation. There are i's in between. Try to verify by yourself that this is here a minus I, and here is the Hermitian conjugate, so there is an I. And this object is the sy Pauli matrix. Okay? So there are three important matrices that appear in this calculation. The 1/2 is there because we are looking at the spin 1/2, but the Pauli matrices do not have this, the 1/2. Okay? These 2x2 things, which maybe I can summarize here. Sigma x being 0 1 1 0, sigma y being 0 minus I 0, and sigma z being 1 minus 1 0 0. Okay, so these three things should be memorized. Okay, I do not insist in memorizing things, but the three Pauli matrices, please try to memorize them. Okay. Okay, good. Now, what else? Okay, let us revisit the question of calculating let us revisit the issue of calculating matrix elements. So suppose that I again ask, we already did the calculation like this, but let me insist a little bit. Suppose that I ask you, okay, calculate psi spin, an operator, the spin operator as alpha psi spin. Okay? Then what I can do is always the following. I insert here, so I have a generic state now, okay, not the sigma and sigma prime, a generic spin state. So I insert here the identity, and I write this as sum over sigma and sum over sigma prime of psi spin, sigma, sigma, or sigma prime, let me call it this sigma prime, S alpha, sigma, sigma, psi spin. Is it clear, right? I just inserted identities in the form of sum over sigma, sigma, sigma. Okay? We have learned how to do that in German. Now, these are the elements that we just calculated. And this object here are, if you remember, I erased them, the elements, so alpha, sigma, times psi spin is equal to z sigma. Okay? The element here. In fact, this object. Okay? So I'm simply writing here sigma instead of plus minus. Okay. So this object is in fact what? It is in fact the sum of the matrix that I just calculated. So S, say alpha, okay, element sigma prime sigma, okay, times what? Times another matrix, okay? Obviously it will be a sum over sigma sigma prime. Let me rewrite these two other things, okay, in the following way. It is sigma prime, sigma psi spin, I just rearrange, okay? Sigma prime. This I put it here, and this I put it there. Do you agree, right? Okay. Now, I will call this object rho of sigma prime. Okay? If I do that, the object that you have here is simply the trace of the matrix for S alpha times the row matrix, right? It's a trace. You see, I multiplied this times that, and this times that, sum. Okay? Now, what is this? This is nothing but the element sigma prime of the projection operator, right? That I might here call it rho. Okay? Rho, for me, for a while, will be simply the projection operator on the state psi spin. Okay? And as you know, this is nothing but psi spin, psi spin. Is it clear? Okay? Now, this is called the pure state density matrix. Okay? So later on we will call those rho things density matrices, but in this case it's really associated to a pure state psi spin. Now, calculating the expectation value of an operator, okay, is always done in this way. Take the trace of the matrix for the operator and the appropriate density matrix describing the state of the system. In this case is again a pure state density matrix, but later on we will generalize it. Okay? Now, this reshuffling is very, very general. Okay? What I have done here for the spin operator and the spin states, I could do it, in fact, for any operator in any Hilbert space. Okay? Again, calculating somehow, I don't want to spend too much time on that at this time, but just to remind you that if I ask you, please calculate this object on any Hilbert space, any operator, then you can also write this as the sum over n prime of the matrix representing A on n prime times the matrix rho, okay, n prime n, where this object here is the pure state density matrix psi. Okay? So in this setting, this is still the projector on the state psi. Okay? So averages, we will see later on that these are connected to measurement, average measurements, okay, are calculated by essentially trace of the matrix of A times the density matrix. Okay? Good. More about this later on. For the time being, I want to stress some properties of this rho operator. Okay? It is emission. Okay? So rho is equal to rho. It's obvious. It's a projection operator, and I know you know that the projection are emission operators. So if you switch these two things, it's the same thing. So this is property A. It's pretty simple. Property B. Rho is non-negative, which means that if I take the scalar element, the matrix element of rho on any state phi, then that's greater or equal to 0. How do you prove this? Well, from this expression, you see immediately that this object is equal to phi, psi, whatever. If you want, I can do it for this psi spin, but it's any psi, in fact, is okay. Okay? So this is the square modulus of psi phi. Okay? So it's greater or equal to 0. C. The trace of the matrix representing rho is equal to 1. I will show you in a second. And the last is that rho square is equal to rho. Now, since this is a projector at this level, P square is equal to P, okay? All projectors have this. Proving this, it takes very little. The trace of rho, let me write it, is equal to the sum over any basis phi n of the projector, which is psi, phi n, okay? Now I rearrange these two things, exchanging them. Sum over n of psi phi n psi. Now I recognize that this is an identity, because this is a basis of the space, and therefore this object is psi, which is 1. Okay? So the trace of the pure state density matrix is 1, and the square is equal to the rho, and it's non-negative under Misch. Okay. This is just rewriting pure states in terms of this funny-looking object. Later on, we will learn that in fact you can write mixed states, okay, which are not projectors. And these are very, very useful when you describe a system composed of two parts and you're looking at only one piece of it, okay? Or in statistical mechanics, for instance. Some of these properties will survive, like this will survive, this will survive, this will survive, but in general, these mixed states that we will describe are not projectors, so they are not equal to this, okay? Now you might ask, where does this come in my spin case? Remember, and here comes the story about orbital and spin that I told you before. If I consider orbital as spin, the wave function of my system is not this. And even if I consider the matrix element of the spin operator, okay, I have to consider matrix element with the full function, okay? Let's try to see what comes, okay? So this is the object that I would like now to address. There's not much space. Nevertheless, I erase temporarily the four properties, and if necessary I will reinstall them. Okay. Now, the goal is the following. I have some psi, and I want to calculate the identity for the orbital times the spin operator alpha and the psi. Okay? And I remind you, okay, that in general psi is different from an orbital part times a spin part. Okay? Let's first do the simple case. Suppose that it was equal. Okay? Then how do I calculate this number? Well, the orbital part looks at the identity and it takes the scalar product with the identical object on the left, and so it disappears. So, for factorized wave function, this object is precisely the object we calculated before, okay? So it is equal to the psi spin S alpha psi spin, okay, which is equal to the trace of the matrix, the 2 by 2 matrix representing the spin alpha, and the 2 by 2 matrix representing the pure projector on the spin state rho. Exactly what I wrote there. Okay? So, same identical calculation. So, the density matrix that appears here will be a pure state density matrix, a projector. But now, let me just do the general case. How do I do the general case? Well, I do the following. Follow me, okay? because this is probably one of the simplest way to appreciate how a mixed density matrix, so a non-pure density matrix, emerges. By the very simple fact that I want to calculate the matrix element of a spin, but there is also some other piece of wave function which I don't care, but it's there, okay? And when you calculate the scalar products, you will see that the resulting object can be put in this form, but this object is not a pure projection. So bear with me for a second. So the calculation goes as follows: 1 orbital times S alpha psi. Okay? So now let me now insert identities here and here. And the identities are made by, well, I write it and you will realize what they are made of. Sum over sigma and sigma prime, integral over dx prime and over dx. And then I have psi here. Then I have x prime, sigma prime. This is the product state that I was discussing before. Position eigenstate x prime as sigma prime, and then I have x prime, sigma prime, and identity in the orbital, and the spin, and then x and sigma, and then the psi. Okay? I simply inserted this identity, you see, with the integral and the sum, and this identity, you see that there is an integral and the sum. Okay? Good. Now, what about this object here? There is an identity in orbital space, and there is x and x prime. So what do you think this is? It's the delta function of x prime minus x times the sigma prime S alpha sigma, the matrix that we calculated already before here. Okay? Good. So, using this delta function, you rewrite this object as the sum over sigma prime and sigma, the integral over a single x, and then I have what? If you remember, this object, I did the algebra at the beginning, was called psi sigma of x. Okay? In general, not a factorized function, orbital times spin, but a spin orbital, so-called psi sigma of x. Okay? So now I have here what? I have psi star of sigma prime of x. X is the same as x prime because of the delta, and then I have psi sigma of x, which comes from here, and then I have the matrix element of the spin. Okay, sigma prime, sigma. Is this calculation so far clear? It's useful, extremely useful. Okay, very good. Now, what is this object here? You can view it as a scalar product, right? So this is the scalar product of psi sigma prime with psi sigma. Okay, now we have it. So my full matrix expectation value can be written as following: sum over sigma prime and sigma of psi sigma prime psi sigma times S alpha sigma prime sigma. Okay? Good. Can I put it in the form that I used there? Of course I can. But this is still the trace. These are 2 by 2 sums, you see? Because these are 2 orbitals. Okay. So it's the trace of S, the matrix of S alpha
times a matrix that I will call rho, okay? But let's see what the matrix for rho is. I write it here. Well, maybe I write it here. The matrix for rho, sigma prime, is equal to simply the psi sigma prime, psi sigma, what you have there. Okay, and if I write it explicitly, is the following 2 by 2 object. Is psi plus, psi minus, psi plus, okay, and psi minus, psi plus star, and psi minus, psi minus. Is it clear? Okay? Simply looking at this expression. Now, let's, well, first of all, it's Hermitian, right? It's an Hermitian matrix, because this is the start of that. What about the trace? The trace is psi plus, plus, psi minus. You can verify with the definition that we gave to psi plus and psi minus that the trace is indeed 1. Okay? But one thing that we still miss is whether this is representable in a simple way like this. Is there a projector somehow of this, of which this is just the 2 by 2 matrix? And the answer is certainly not. In fact, let me consider the physically very useful case where psi minus is in fact orthogonal to psi plus. Okay? The two spin orbitals might be well orthogonal. In the spin orbit coupling case, we will see that they are composed of different orbital angular momentum wave functions. Okay? So if the two orbitals are orthogonal, here I have 0, and here I have 0. And this is a number which I will call W plus, is the weight associated to the plus, and this is the weight associated to the minus. So the 2 by 2 matrix is W plus, W minus, 0 and 0. The sum of these are two real numbers whose sum is 1. Okay? Good. Take the square of a matrix of that form. The square of the matrix, okay, or the matrix element of the square is equal to W plus square, W minus square. Now, obviously, if these are different from 0 or 1, the square of a number less than 1 is in general different from. Okay, so you immediately realize that if I have a spin orbital wave function, and I look only at the spin, somehow tracing out the orbital part, then the resulting matrix element for density matrix for the spin is a mixed state, so-called, so is not a pure spin. Okay? This is the first appearance of mixed states. Later on, Professor Fazio will discuss these things in a more general context. But I wanted to present to you how they might emerge in a very innocent way by just disregarding some piece of information, the orbital part, when you want to calculate the spin matrix elements. Okay? Questions so far? Good. Now, yeah, we have a little bit more, so I can. You're presumably very tired, but we have to insist because unfortunately time is running by fast. So the first thing that I would like to discuss with you is how you prepare spin states. I told you that if you make a hole in a Stern-Gerlach apparatus, you create a Stern-Gerlach filter Okay? So if I have the z direction and I put the hole in the appropriate spot, all the spins coming out are pointing out. Okay? Remember the thing? Okay? So there was an axis, z axis, and there was a hole here, and the spin up, a spin down go here, and the spin up go here. So all you have here is spin states aligned with the axis of the apparatus. Okay? This is a very nice trick. Indeed. Suppose that I have, this is z, but this is x, and this is y, and you send the spin through the apparatus along y. Now, if the apparatus is aligned along z, obviously what you get at the end is pure spin-up state. But, here comes the magic. You can in fact rotate the apparatus, okay? For instance, at an angle theta on the z-x plane. And then you are guaranteed that what you get here are spins aligned along that direction. Now, you might start wondering, what is a spin aligned along a certain direction? N, okay? And in fact, let me just do it slightly more in general. Let's consider the following object, n dot sigma. N is a vector in space, actually a unit vector in space. Therefore, okay, you give it to me if you tell me theta, and in general, okay, if it is here, in general you give me phi. The usual spherical coordinate thing, except that now the modulus is 1. Okay, so n is sine theta cos phi in general, sine theta sine phi, and cos theta, the three components. This is the three elements of the spin operator. If you calculate the element in the 2x2 representation, you would obtain the following thing. Essentially, sine theta cos phi times the metric for sigma for Sx, which is 1/2 times the Pauli matrix X, plus sine theta sine phi times 1/2 the Pauli matrix Y, plus cos theta times 1/2 the Pauli matrix Z. Okay? This is the matrix element of the spin in a generic direction. Let's do the calculation. So there is a 1/2. On the diagonal there is only sigma z, and therefore here I have cos theta, and here I have minus cos theta. On the off diagonal, let's look at this element only, because the other is the star. I have sine theta cos phi, okay, multiplying the 1, and then I have minus I sine theta sine phi, and here I have the star. Okay? What is this? 1/2 cos theta minus cos theta, and here is sine theta times e to the minus I phi, and here sine theta e to the I phi. Is it clear? Okay? This is the matrix of the spin in a generic direction, theta and phi. If you take phi equals 0 and theta equal to 0, you obtain sigma z. If you take phi equals 0 and theta equal to pi over 2, for instance, you get 0, 0, 1, 1. Okay? And you get this. If you take phi equal to pi over 2 and theta equal to pi over 2, you obtain 0, 0. Here I get 1, 1, but here I have e to the minus I pi over 2, which is minus I, and here I have plus I. I get sigma y. So this is somehow the generalization of these three objects to any arbitrary direction in spin space. Okay? That's very useful sometimes. And now I can ask you, what are the eigenstates and the eigenvalue of this object? This is, after all, a spin operator aligned in a certain direction. You must have eigenvalues and eigenvectors. Now, the eigenvalues you expect is plus or minus 1/2 again. It doesn't really matter which direction you pick up to quantize your, as preferred direction in which you write your eigenstates. But the eigenstates are kind of tricky to write. In particular, you see that here I have only cosine and sine. And I ask you to do as an exercise to show that the following state, so it's the plus 1/2 spin state in the direction n, is cosine of theta over 2 times the plus along z plus the sine of theta over 2 times e to the I phi times the minus along z, and the minus 1/2 n is equal to sine of theta over 2 e to the minus I phi plus minus cosine of theta over 2 minus. Okay? In other words, this object here are the elements of a two-component spinor. One is cos theta over 2 and the other is sine theta over 2 e to the I phi. I ask you to take this two-component object to multiply by this matrix. So this matrix times this object here, okay, and prove that the result is plus 1/2 the same object. Okay? So please verify that indeed this is an eigenstate of the spin along n with eigenvalue plus 1/2. Okay? I prefer to do this rather than to ask you directly, please try and find the eigenvalues of the eigenvector of this 2x2 matrix. It's a 2x2 matrix. So something that you can handle, right? And if you try to find the eigenvectors and eigenvalues, you will find eigenvalues plus or minus 1/2. Eigenvectors, you will see that there are lots of choices of phase that you can make. And one particular choice of phase is this. Okay? And accompanied to that, there is this other vector here, which you can write as a 2x2 object as theta over 2 e to the minus I phi and minus cos theta over 2. Okay? So again, if I put this here, I will find minus 1/2 the same object here. Okay? Try to verify. Now, let's pause for a second. Suppose that I have theta equal to pi, so I'm looking close to the south pole, okay, this is the Earth. Theta is equal to pi. Now, when theta is equal to pi, let's look at this expression. The cosine of pi over 2 is 0. The sine is 1. And the function is e to the I phi. Now, you know that the value of phi at the south pole should be not relevant, because, I mean, you don't turn around the point. Okay? So somehow this function here is funny at the south pole. It's not well defined. Okay? On the contrary, it's perfectly well defined at the north pole, because the north pole has theta equal to 0, and at theta equal to 0, the sign goes away. And therefore, this e to the I phi there is not very important. You might say, ah, disturbing, yes, but so what? Well, let me just make you notice the following fact. I could write an entirely legitimate expression for my eigenstates. Please verify in the following way. Just cosine theta over 2 e to the minus I phi and sine of theta over 2. Okay? This is as good as this. I simply multiplied the state, both components, by e to the minus I phi. You see? And here I make it disappear, and here I make it appear. And equally well, instead of this, you might consider the following state: sine theta over 2 and minus cosine theta over 2 e to the I phi. What did I do to get from here to here? Just multiply by e to the I phi. Here you make 1, and here you have e to the I phi. Verify. They are equally good eigenstates. I mean, doesn't really matter, obviously. You are multiplying both components by a number, so if the algebra of matrix product was working there, it will work as well, right? Well, what's the difference? Let's look at this function now at the south pole. So theta is equal to pi. Now, this is 0 at the south pole, and this is 1. So the function is perfectly well defined. It's a 0-1 function. And what about this? At the south pole, this is 1, and this is 0. Fantastic. So it's a very good function. No ambiguity of phi. So somehow, this function is good around the south pole and everywhere except at the north pole. If you look at the north pole, theta is equal to 0. This is 1. And this is ugly face. And this is 0. Okay? So, on the sphere of the spin, south and north pole are kind of singular representations in terms of spherical angles, theta and phi, and the spinors fill this singularity. You cannot find a unique representation of the spinors which is regular everywhere. Okay? Somewhere they show to you some funny object like this. Okay? Now you might think that this is just a little game, but I can assure you that this is one of the roots of topological insulators. Okay? Believe it or not, the fact that there is no unique representation of the spinor wave function that is good everywhere is in fact at the basis of the fact that the Haldane model has a non-trivial topological phase. Believe it or not. Okay? So do not take this as simple-minded exercises. That these are in fact things that recently people have discovered to be of some importance in actual physics. Okay? The Haldane model is essentially all based on this. You might ask, why is the Haldane? Well, the Haldane model is a model of electrons hopping on a honeycomb lattice. Okay? The hexagonal lattice. Now, you have done solid state already, right? A little bit. And you remember that honeycomb is not a Bravais lattice, right? There is a two-component basis. The A and the B sublattice. Good. A two-component object to tell me how much wave function I have there. That's the pseudo-spin two-component object that is important in the game. In the game, this physics enters there and governs a non-trivial topology in an insulator made of graphene. Okay? So this is just vague things, but just to somehow make you curious about, the non-trivial aspects that are behind this Inoxen-looking arguments about multiply by phase, see, okay? So I stop the discussion here, but take it seriously. Okay. Oh, good. Now, I want to just give me, say, 10 minutes, okay, at most, to finish the story that I wanted to tell you today. And the story goes as follows. Suppose that I have now a system, okay, an hydrogen atom or whatever. We still have no knowledge of what the hydrogen atom is exactly. But essentially I have some Hamiltonian, the orbital part, I call it H0, okay? And then I have some G0, mu B, BZ, okay? A magnetic field around Z, and here I have sigma Z, okay? So I put my system in a magnetic field around Z. There is no coupling of orbital and spin, so if I have some eigenvalue of this object, En, you know that in fact it is two-fold degenerate, because I can think of it as with spin up or with spin down, right? By associating a different part of the, so somehow to this I associate an orbital part, okay? But I can always multiply by up or down. Is it clear? These are two states. They are orthogonal. They are factorized, by the way. There are no finite spin orbitals before. Very simple things, but they are two. And they have the same energy, En. In absence of magnetic field. Once you turn a magnetic field, one of them goes up linearly in B, and one goes down linearly in B. So this is the BZ axis, okay? So what happens? Let's see. The BZ positive, okay, makes the up to go here. So the up gets higher energy, and the down has lower energy. By the way, this is at the roots of nuclear magnetic resonance. Okay? You put the magnetic field, okay? You create a Zeeman splitting of spins of nuclei, not electronic, spins of nuclei in your body. And then you send a radio frequency. These are small, very, very small splittings of levels, okay? They require very low frequency things to excite one up to there, okay? So by sending some radio frequency, you can actually induce a transition from down to up, okay? When this happens, the radio frequency is absorbed, okay? So by mapping what is the frequency at which there is absorption, you know precisely what is the splittings of levels at that point in your body. And believe it or not, I mean, the technique is so much advanced that I can precisely map this and get an image of the part of the body that I want to see. Because there are different nuclei of interest where the precise values of these splittings are. I mean, there is a whole science obviously behind, but just to tell you that this innocent fact of Zeeman splitting of levels is in fact at the root of nuclear magnetic resonance. Let's skip. Let's move on. Good. Now, incidentally, this factor 2 that you have here with the factor 1/2 that you have there, they just cancel. So if I use Pauli matrices instead of sigma z, here they are, okay? The 2 goes away, okay? So this object is plus mu bb. Let's omit the z because it's around z. And this is minus mu bb. Is it clear? Mu b is the Bohr magnet. All right. Now, suppose that I have formed a state at time t equals 0, which is a factorized state, where, for instance, I have in the ground state or in some whatever state, okay? And then I have the spin part is not along z, however. is along the state that I just discussed before. Eigenstate of plus spin along the direction n. You remember the 2 by 2 object that I wrote for you before? Okay. So n is given by some theta 0 and some phi 0, right? Some angle theta and phi in spin space, okay? And here I have that object, so let me write explicitly what it is. It is the cosine of theta 0 over 2, the plus the sine of theta 0 over 2 e to the I phi 0, the minus. Okay? Alright, now let's see what happens as time passes. So to calculate the evolution, I should multiply this object by e to the minus I, the Hamiltonian, times t over h bar, here, right? Remember the evolution operator, exponential of the Hamiltonian. Now the Hamiltonian is sum of 2 parts, and these 2 parts commute. One works on the Hilbert space of the orbit, and one works on the Hilbert space of the spin. So you split them. Good. Which means that here I have e to the minus en t over h bar times phi n. But most interestingly, here I have e to the minus I mu b b t over h bar sigma z. Do you agree with me? This is the Hamiltonian term that I have to put there, times t over h bar, and then I have to multiply this funny looking object. Plus e to the I phi minus. We are almost done, don't worry. I know that you are thinking about having lunch or I'm almost done. Now, this is a face in front of the wave function, not particularly important. But you see this object here, it acts in a different way on the plus state and on the minus state. Let's see the action. Okay? The action of this, so I write this the same, is cosine theta 0 over 2 times on the up state, this is an eigenstate of sigma z, right? And therefore here you can put e to the minus I mu bb t over h bar times the plus. Okay. Plus sine theta 0 over 2 e to the I phi 0, the original direction, times. Now I have the minus here, which means that here I have a different sign, e to the plus I mu bb t over h bar minus. Did you follow so far? Did you follow? Okay. Now, I can take this factor out if I really like. But if I do it, I have to pay the price. Okay? So let me write this in the following way. This object as before times e to the minus I mu bb t over h bar, and then I have cosine of theta 0 over 2 times the plus sine of theta 0 over 2 e to the I phi 0, the original thing, times e to the 2I mu b t over h bar. Okay? Minus. Now, tell me, what is this? It's a spin, eigenstate, but in which direction? Remember how to, if you remember the expressions I have, the angle phi is essentially the phase that I have there. Originally it was just phi 0. Now you see that it's as if this phi 0 turned into a phi of t, which is phi 0 plus 2 mu b divided by h bar times t. Is it right? Okay? So it's a spin pointing at a new angle phi, not phi 0. But theta 0 is the same. Okay? So I put the magnetic field there. I start with the spin oriented around theta 0 with a certain angle phi 0. And what happens as a function of time? Precession. Okay? So the spin precesses around z. With what angular velocity? So, quasi finito. Eh? This object. This is an angular velocity. Now, you should remember that mu b is E. It collects already the h bar of the angular momentum, and then there is 2mc. And now you see clearly that h bar and h bar goes, okay? So this object is in fact, and the 2 goes, by the way, E b over mc. This is called the Larmor frequency. Okay? Is in fact the frequency with which a charged particle would turn around a magnetic field due to the Lorentz force. Okay? So the spin precesses with exactly the Larmor frequency around the z-axis. Okay? I think we should stop here. But yes, and by the way, twice that object is precisely the energy difference between the two levels. Okay? Divided by h bar. So somehow the frequency with which the thing rotates is precisely the difference in energy between these two states. This is an always come back. Somehow the reason why light is absorbed by atoms is because difference between energy levels are indeed very sensitive to any perturbation at that frequency. It's a kind of resonance that occurs. Okay? So in this case, this is the frequency with which the thing turns. If you excite with an external radio frequency precisely at that frequency, the system gets mad, okay? Because you get in resonance, and it happens that even if I have a state in here, I can flip it, okay? So there are funny resonance phenomena that can occur. But this basic rotation of spin is probably the simplest example of dynamics of a spin. Okay, we stop here, and we'll see tomorrow. It's a strange day after